Hi, I'm John McMillan, and welcome to today's webinar demonstrating rigid flex technology in PAS Professional. From cell phones and wearables to IoT devices and in every industry, more products are requiring both static and dynamic rigid flexible circuits than ever. In fact, rigid flex designs not only eliminate the connectors and improves performance and reliability of electronics designs, it empowers companies to meet today's most challenging form factor requirements. So, if you thought that first pass success with a correct by construction process for rigid flex designs from stack-up definition through to manufacturing handoff was impossible, you'd better think twice. So, to demonstrate how you can simplify the process of creating complex rigid flex designs and save both design cost and time using PAS Professional's advanced rigid flex technology, I'll turn this webinar over to one of our technical marketing engineers, Brent Klingforth. Brent?
Thank you, John. As you mentioned, simplifying the design process is something we all are striving for. With more tasks being placed on us than in the past, we all need faster and better ways to get our jobs done. Creating designs using flex technology is a design process that has been overlooked by the industry for some time. Engineers have historically used MCAD tools to design their simple or very complex flex or rigid flex designs. If you've been in this boat, you know what all the headaches are in using a tool with little or no knowledge of electrical interconnect and design rule checking. On that topic, let's take a quick look at what challenges there are when designing a flex circuit over a rigid PCB. Trace routing should be done with arced corners instead of 90s and 45s. All entry and exit component solder pads and vias need to use teardrops. No components or vias should be placed in a flex bend area. Traces need to run perpendicular to the bend area. Do not change trace width or direction in the bend area. Use rounded corners on rectangular or square land pattern pads. Several more will be discussed during our demonstration. All these special design requirements can be achieved with any PCB or MCAD tool. My question to you is, how efficient will you be creating your design? We are all human, mistakes happen. How much time do you think will be spent verifying you didn't make mistakes? While you're following along today, keep in mind these challenges and reflect back on those you've experienced in the past for those with previous experience. Before we move into a design, let's cover what the different types of flex and rigid flex designs are common today. Type 1 is the simplest structure containing only one conductive layer with a cover layer on top and bottom. Type 2 has two conductive layers, insulated on top and bottom, can include vias, and through-hole and SMD components. Type 3 is three or more conductive layers, through and blind and buried vias, and through and SMD components. Type 4 is a combination of flex and rigid PCB. One or more flex layers, vias, through or SMD components can be included. And Type 5 is two or more conductive layers, vias allowed but not plated through. Vias can be accessed from any layer with exposed openings in all layers. In our example today, we're going to create a small drill with a rugged LCD display and Bluetooth connectivity. The LCD will take advantage of cost-saving flex technology by removing two connectors and cable assembly. The Bluetooth board will also be attached via a flex interconnect. We haven't created the PCB yet, so we're going to start from the schematic. We'll review the new circuitry that we have added, which in this case is the Bluetooth circuit. We'll then activate the Start PCB function from the schematic tool. From this dialog box, we can choose what PCB type we want to create, a regular rigid PCB or a rigid flex combination. Next, we'll choose a template from the template list. In this case, I'm going to choose a 6-layer stackup. Templates help us save time by setting up basic functions that we normally have to do for every design anyway, like board stackup, board outline, documentation. Once our design has fully forward annotated, we can see the stackup that was imported via the display control. Let's take a detailed look at the stackup which was imported via the template. As we can see, there's very detailed mechanical and electrical information about the stackup. If we select one of the cells under the layer type, you can see the various types that can be assigned. Since I know this design is using edge fingers to connect to a connector, I need to add a new layer for the stiffener that's required. Once added, I'm going to give this layer an identifying name. Next, we're going to adjust the thickness of the stiffener layer. This number will be based on our vendor's data sheet to ensure the flex fits properly into the connector. Once completed, this new layer appears in the display control. To create the board and flex areas for this design, we'll be importing intelligent data from our mechanical engineer who is using NX. Most designs are started from drawings, which is time-consuming to reproduce and error-prone. Using the industry standard IDX data format, our mechanical engineer can export the board and flex outlines they have created that match the mechanical enclosure and mounting. If your company is not using an MCAD tool that can export IDX, a board outline can still be auto-generated from a step file, saving us valuable design time. From the 3D window, we will activate the ECAD-MCAD collaboration interface. This will allow us to import the board and flex areas along with the mounting hole to hold the board in place. After selecting the file our mechanical engineers created, we can see the items that will be imported. In less than a few seconds, we have 2 boards and 2 flex areas created. While in the 3D window, we can inspect the board areas. An added automation feature in Path Professional, which assists with DRC and plane generation, is a design object called Route Border. This object can be auto-generated using a setback, relieving us from spending valuable time drawing a complex shape. One of the most important features of a modern ECAD tool in regards to flex design automation is assigning intelligent stack-up information to each region of the board. Here we will double-click the LCD display flex region, give it a label, and then choose the layers that will be used to manufacture this section. This is a section that will connect to the external board and require a different stack-up definition than region 2 due to the added stiffener. To make sure we've selected the correct layers, we can open the stack-up dialog box for review. To simplify this process even further for those that have many flex regions in a design, we can create stack-up schemes. These will assign stack-up configurations to a name that you can pick from when selecting the areas in the design, or assign them via the scheme dialog box. Let's create 2 stack-up schemes for this design. The first will be for the LCD flex section, and the second for the Bluetooth. Next, the stack-up layers need to be assigned to each scheme. For the Bluetooth section, the cover layers, adhesive layers, and flex core will be chosen. For the LCD section, cover layers, adhesive layers, flex core, and stiffener will be chosen. Lastly, the appropriate regions will be assigned to each scheme. To verify our assignments, we can select each region and see the scheme assigned via the Properties dialog. Stack-up information does not only provide the overall thickness for each section of the boards and flex regions, it also provides information for design rule checking, collaboration, documentation, intelligent components, and manufacturing. To visualize this design as a completed product, we will import the drill enclosure for this electrical design. From the 3D window, we will import the step model of the drill enclosure and items the PCB and flex will interface with. Using intelligent mating, we can align the PCB with the mechanical model. To assist with viewing the board and the mechanical model, we can change the color or transparency, making it easier to view the board inside the enclosure. While in this view, we will also notice the layer thickness for each region has now adjusted based on the stack-up assigned to that region. Now that we have board areas assigned to stack-up regions, we need to create the bend areas. Bend area definition is the second most important feature available in modern ECAD tool when working with flexible PCBs. These areas allow you to visualize the design and create virtual model of the board in conjunction with the mechanical design. From the draw menu, select bend region. A dialog will appear with options you define for each bend region. Once the region has been initially placed, we can now fine-tune the bend angle, width of the bend, and if the bend will start from the center, left, or right. Switching over to the 3D view, we can visualize the flex with the bend area we defined. Path Professional provides an intelligent 3D object viewing icon for interactive rotating of your model and predefined viewing angles. When selecting the blue section on a corner of the cube, your model will adjust to that ISO view. When selecting a surface, your model will adjust to that side view. To help us further define the proper bend area and angle, we will turn on the mechanical model. We can now quickly make adjustments to the bend area via the 2D workspace and see how it affects positioning of the flex and rigid PCB relative to the mechanical enclosure. With the bend dialog box still open, we will also adjust the angle of the bend to ensure the Bluetooth board sits inside our enclosure properly. With the Bluetooth board positioned correctly, we will define the bend areas and parameters for the LCD flex. We'll set up our view so we're looking into the drill case from the back. For this flex to wrap properly in the case, we'll need a minimum of 2 bend areas. To start, we'll place the bend area closest to the PCB. Set the initial bend angle to 90 degrees. Next, a large bend area will be placed in the middle of the long straight section. With a couple of adjustments to the bend area length and angle, we can create a nice arc that positions the end of the flex near the LCD connector. To finish off the bend for this flex area, a third section will be added near the 90-degree turn in the flex. Again, making some quick adjustments to the angle of this bend area will provide a perfect fit for our flex, concluding we have the proper length for assembly and functionality. As you can see, using 3D visualization dramatically cuts the time it takes to create our base geometry for this design. Yes, 3D MCAD tools have the capability to bend objects in view with the enclosure model. However, there's no electrical or manufacturing intelligence when designing flex circuits outside of a modern ECAD tool like PADS Professional. Now that we have the board outline created properly, we can start placing parts on the design. To assist with part placement, PADS Professional provides a Component Explorer panel, making it easy to search for and find components based on groups. In this case, the schematic was created using hierarchical blocks, so our parts are already placed into groups. Selecting the controller group, we can drag J1, the flex finger connector, into the design workspace and place at the end of the flex. Before we move on with this design, let's review some of the intelligence that should be built into component land patterns, eliminating errors when using parts in a rigid flex design. First, we will take a look at the flex finger connector model. Starting the Library Manager application from Pro Layout, we can find the flex finger connector model and open it for editing. This can also be done directly from the design if changes to a land pattern are required for that design. Now viewing the cell, we can see there's a shape that's been added over the fingers, creating an opening in the cover layer. This is similar to creating a gang relief for solder mask on a fine pitch land pattern. Let's take a look at a cell that could be used on either a rigid board area or a flex area. For this 1005 resistor cell, we'll take a look at the pad stack definition being used. We will notice in the pad stack header a tab called Flex. Selecting this tab, we can see there's pads assigned to the top and bottom copper and cover layers. There's also a pad option for stiffener if required for some designs. Now let's see how this information is beneficial to creating a design correctly the first time. In our design, we have a resistor that's been placed in line with one of the LCD data lines. For example purposes only, let's see what happens to the land pattern for this part when we move it from the rigid part of the board to the flex. After placing the resistor next to the finger connectors, notice the copper pads have changed from a rectangular pad with square corners to rectangular pad with rounded corners. This happened automatically with no extra effort on our part, as the proper pad stack information was defined in the cell. Switching our view over to 3D, you will also notice the cover layer openings are proper for the resistor and the finger connector. As you can see, having intelligence built into your StackUp and library parts can prevent simple mistakes from happening later on in the design process. Let's create our design rules before we start routing. Rules are often overlooked or not used to their full potential when designing a PCB. Rules provide the basis for creating a design correctly the first time. When routing a flex circuit, rules for these areas may not be the same as those for the rigid part of the PCB. Allowing the tool to handle all the dirty work of making sure the proper trace widths and spacing are used will only make our lives easier. For this design, we've chosen to use as much real estate as possible in both flex areas to make a highly robust design. As such, we will use rule areas to our advantage. I created a rule area called Flex and set the appropriate trace width and spacing to maximize area usage on the flex. For this, it'll be 10 mil traces and 9.5 spacing between traces. As you've noticed, while we've been reviewing the importance of design rules, using a spreadsheet-based environment makes rule entry quite simple. Another advantage PADS Professional rule environment is the ability to reuse design rules created for one class of nets. Using this matrix allows you to create rule sets that can be used between several classes of nets. If a change happens, you don't have to worry about which classes had the same rules and forget to change one. Change it in one place, and it affects all the classes you've assigned the rule set to. Another concern when routing traces on a flexible circuit is what's called I-beam routing. As you can see from the pictures, this is when a two or more conductive layer flex has traces routed on adjacent layers. You do not want to route them broadside to each other on adjacent layers. This reduces flex of the circuit and induces unwanted tension on both copper layers and the bend area. We just completed our design rules with a rule area defined, so before we can start routing, we need to place this rule area. While doing this, our design team has decided we should place a ground planes in our flex areas. So we will use the shape we created for the rule area to define our planes on the flex by copying and repurposing. When bending a flex, having unequal copper area usage on adjacent layers can lead to higher failure rates. So for our ground planes, we need to crosshatch the copper. To follow best design practices for flex circuits, plane areas should not be created using orthogonal hatching. They should be diamond hatched so that you don't end up with the I-beam effect with traces on adjacent layers. By adding a plane area specifically for the flex allows us to control the copper hatch pattern for just that shape, while the remainder of the design will just use the route border. As I mentioned in the beginning, when routing traces in a flex area, you should only use arced traces. Even though this design may seem simple, routing all these traces to follow the arc on the flex could take some time. Using automation available in Path Professional, we can route one trace which will act as a template for the remaining. While interactive routing, I can switch to arc corners to simplify routing of the first trace. Now that we have our first trace in place, I'll use the multi-hug route feature in Professional to complete the remaining traces. Path Professional includes help videos directly in the tool. Many of the functions available from toolbars will play a video showing how to use that feature when holding the mouse over the button. With hug routing, we can see from the extended tooltip and video the steps required to make this function work. To start, we'll set the graphical net name selection checkbox. Hold the control key, select the first pin to be routed, then the second, and so forth. In the multi-hug dialog box, set the proper spacing edge to edge for the traces. You can multi-select and enter once to fill in the entire column. We'll do the same for the trace width, which for these nets we'll be using 10 mils. After selecting all the pins, select where you'd like the new trace to start on the template trace or object. Then select the termination point. Click on the side of the object you want the new traces to be created. All 9 traces will now appear. To finish off the traces at the edge fingers, draw one new segment and copy-paste to the remaining. To complete these traces, we will use interactive routing, not point and click like most people may use today. Being able to guide the trace into place without worrying about each corner allows you to get your job done faster with the same quality as point and click. To start, we need to fan out the nets on this part so we can properly position vias for routing. This is quickly achieved by selecting the pins or component to fan out. Right-click, apply fan-out pattern. Now we can adjust the power and ground fan-out and complete the nets on the bottom layer. Next, we will route each of the signal nets from the partially routed traces created during hug route. As we start routing these nets, notice the trace width change from the flex area to the rigid board. This is caused by the rule area we created earlier. By using this capability, I do not have to worry about changing the trace width by hand each time I start one of these traces. The other advantage is traces routed in the rigid area are now using a smaller clearance rule so they don't consume too much space. This shows the power of using design rules to your advantage instead of doing everything by hand. Also notice while routing how easy it is to guide a trace into a tight spot and let the tool do all the work by pushing and shoving others out of the way, given there's room to do so. After all the routing is completed, we can move vias around to clean up areas we do not like or felt could be done a better way by simply moving the via to a new location, while the tool moves other objects around to accommodate what we're doing. Now that we've done some routing, let's go ahead and work on the plane areas on this design. Earlier, we created a plane area specifically for this flex. But for the remainder of the design, we're just going to use the route border. To do this, we can go to the Planes menu, Plane Assignments. From this dialog box, we can assign what layers are going to be plane layers and what nets are going to be assigned to those individual layers. On layer 3, we will assign the net name 5 volts. Another automation feature related to plane areas in Paths Professional is using what's called dynamic planes. After we set up our layers for dynamic, the plane areas will automatically flood. Notice that the flex area is a crosshatch pattern, like we defined earlier when we created the shape. We can go in and customize that shape again by selecting the plane area outline, selecting the hatch options tab, and then I can adjust the trace width, the distance that it's going to draw the lines in the trace width. I can change the hatch pattern. I can also tell the tool to automatically fill in non-full square sections to ensure that I don't have any acid traps during the fabrication process. Let's take a quick look at what our planes and traces look like in the 3D space. And we can see the traces in the design, and if we roll it over, we can see the hatch pattern on the bottom. In the Bluetooth section, we have 5 volts that needs to go over to the Bluetooth board to generate our voltage for the Bluetooth receiver. So instead of routing traces, we're just going to let the plane go across. And to prevent the entire layer from turning into a copper plane, we're going to put a planeage struct over that layer and only allow a certain width of copper to flow across to the next board. The next section of the board we'll be working on is the Bluetooth section. You will notice there are no parts placed in this section yet. Because we've created a Bluetooth transmitter and receiver previously in some of our other designs, we would like to reuse that content. To bring in our reuse circuit, we will use the Layout Circuit Clipboard feature from the Edit menu. We'll click the Open File button, navigate to the folder where our circuit is that we saved out from another design, select that item in the dialog box, and hit Paste. The circuit will then attach to our cursor, and we can position it appropriately within the board area. Notice when the circuit is placed into the board area that the plane areas automatically flood. Because we've defined the brout border as a plane area, and now that there's ground vias going through the ground plane, it automatically flooded. In addition, if there were planes included with the reuse circuit, those will also have been placed and flooded. If we zoom into the flex area, we'll notice that the ground planes have merged across the flex and also have filled in with a hatch pattern very much like the LCD flex that we defined earlier. Design reuse is a tremendous time saver, as you can see here from the Bluetooth circuit that we brought in. Keep this in mind the next time you're starting a new project, and think about other circuits you can use from another design. Now that we've nearly completed the design, let's take a quick look in 3D. You'll notice all the parts have full 3D models. That's because we've assigned models to all of our components and stored them off in the library. Now, by activating the bend feature, we can see what the design will actually look like inside the end product, with the flexes folded into their final positions. You'll notice we're missing one feature on the LCD flex, and that is the stiffener. So let's go ahead and create that. Before we do so, let's cover why we need a stiffener in this area. When using edge fingers on terminating end of a flex for board interconnect, there are a few special design requirements that should be followed. First and most important is the addition of a stiffener on the back side of the flex under the edge fingers. As you can see in the diagram, the stiffener needs to extend past the length of the edge fingers. A minimum of 0.30 inches is recommended. For the thickness of the stiffener, consult the mating connector's manufacturer documentation. The stiffener provides a couple different product reliability features. One, it allows the flex to fit tightly into the connector. And two, if the flex bends in that area, it can prevent cracking where the traces route into the actual edge fingers. So as you can see, the stiffener is just a draw object that's placed on the stiffener layer that we defined in the stack up. Because this drawing's been placed on a layer that's been tagged as the stiffener, when we move over to the 3D view and check the box for display stiffener, it will then appear on the flex. Let's now take a quick look at what the stiffener looks like. So if we zoom in and look at it from a side profile, we can see where the cover layer clearance is, we can see where the edge fingers are, and then we can see where the stiffener is overlaying on the top of those. Zooming back out and looking at the design in full view again, let's take a look at how the finished product looks inside the drill enclosure. Turning the drill enclosure back on, we can see where the board sits inside the drill. But to get a better look to see how everything really fits inside the drill, we can do cross-section views. From the back side, We can do a cross-section view where we can look at the LCD flex going up into the LCD display. We can then turn the drill sideways and do a cross-section and see how the Bluetooth board sits up against the backside of the drill. Now that the design is near complete, the mechanical engineer would like a copy to place inside his model. Using the ECAD-MCAD collaboration tools, we can generate output including all of the 3D models of the components to pass along to the mechanical engineer. To control what information is sent to mechanical engineering, we can filter out objects that we don't want sent over. Once the filter has been set, we can refresh the display and then review all of the content that will be passed through the IDX file. Before setting the information, we will set the file name to something that matches the description of what this file contains. The mechanical engineer will create a new assembly and import the IDX data into this assembly. By bringing in the electrical data as an assembly, the mechanical engineer will be able to move components and adjust the board if needed. There are some additional benefits by using PADS Professional and NX. PADS Professional can generate all of the 3D model content that's in the electrical design, and NX can then import all of that 3D model content. Before doing so, we'll take a quick look at all of the data that transferred over via the IDX. The electrical engineer turned on all features of the PCB to pass across to mechanical. Part of that being they wanted a full picture of the design for visualization. Since this is a drill and there'll be a fair amount of heat generated, they want to be able to do simulation to determine if any additional heat sinking is required. Once all the flex areas have been adjusted appropriately, the mechanical engineer can then mate electrical assembly with the mechanical assembly. And using technology in NX, he can perform his own verification for fit and finish. Along with creating visual files for various reasons, the mechanical engineer will be able to create intelligent documentation using an intelligent model of the electrical content. Now that we're done with the design and the team has approved all the mechanical and electrical fit and finish, we can generate the final output to send to manufacturing. Using ODB++, we can generate a fully intelligent model of the printed circuit board in Flex for both manufacturing the raw board and also for assembly. As an added benefit of using this technology, PADS Professional includes an ODB++ viewer that can automatically be opened and view the ODB++ data after it's been created. When viewing the ODB++ content, you can see the intelligent information that was included, like the bend areas, each one of the rigid and flex areas, the stiffener, the cover lay areas are all included in the model, so that less documentation has to be created. In addition to just viewing the ODB++ data, PADS Professional also generates the Gerber data and loads that data into the ODB++ viewer. So if you don't feel confident with ODB++ for some reason, you can do a compare between the Gerber and ODB. To recap, we discussed how to remove the cable and connector from a smart drill, resulting in easier assembly and lower cost. This is only one example of how flex circuits provide a benefit. Here's additional items to think about when designing your next product where flex circuits may provide a better solution than conventional design techniques. Product needs to be lighter. Shock and vibration are an issue. Product needs to work in very high or low temperatures. Polyimide temperature range is -250 to 400 C, where FR4 is -50 to 110. Cost of board-to-board connector cable assemblies is an issue. Future product miniaturization and contemporary product packaging. PADS Professional is a state-of-the-art electrical engineering tool set that provides an intelligent product flow with automation to handle the simplest to most complex designs, including flexible circuits. Professional with Flex adds the following: intelligent footprints, full DRC for flexible circuit design requirements, intelligent stack-up design, comprehensive design rules, routing automation, MCAD-ECAD collaboration, intelligent 3D visualization, and a complete data model for manufacturing.